Okay, and we're recording. Good deal. So last time we were talking about direction of fastest increase and related ideas. So remember, the idea of direction of fastest increase is it's the direction that you should go in the domain such that the rate of increase, namely the directional derivative, is as big as possible. We're trying to maximize this directional derivative. So as big as possible, so that would be, we're talking about the direction of fastest increase. Okay, so we talked about this last time, and we argued that the direction really ought to be, this ideal direction is this right here. It's the direction that the gradient vector points. So the unit vector pointing in the same direction as the gradient vector. Then we asked the related question, if you are in fact going in that direction. Let me zoom so you can see better. If you are going in that optimal direction. So that it is the direction of fastest increase. Well, how fast is the function increasing if this is in fact as fast as it can be increasing? So we did that calculation. We computed that corresponding directional derivative, and the punchline is it's the magnitude of the gradient. And I think this is where we left off last time. Okay, so we asked a couple of very natural questions. We got a couple of answers that were very crisp, right? The direction of the gradient vector, after all. The magnitude of the gradient vector. Very natural, very crisp. And so I like to think of this as giving an alternative point of view on what a gradient vector is. So up to this point, we've talked about the gradient vector. We defined it as a, algebraic object, but basically our motivation for the gradient was that it was a notational shorthand. It was a convenience. Right? It allowed us to not have to write down a bunch of terms, ... So, notational convenience. Fundamentally algebraic object. Right? So, what we have now is an alternative point of view that's entirely geometric. So, this is what I like to call a geometric characterization of the gradient. So, I'm going to describe the gradient now by way of its defining geometric features, namely what direction does it point and what's its magnitude. Right? Forget about coordinates. This isn't about coordinates. This is about sort of a geometric point of view on the gradient. And geometrically, again, direction and magnitude. Well, the direction is this. It's the direction of fastest increase. Again, rolls off the tongue very nicely. This is a natural thing to want to talk about. And the magnitude is, how steep is the mountain? Right? It's how steep is it in the direction of fastest increase? How steep is it in the direction of steepest ascent? And so, as I like to say then, how steep is the mountain? Okay, so purely geometric characterization, and that's a valuable point of view. All right, how are we doing? Is everybody on board? All right. Okay, so here's an example. We've got a hill, you can see here. It's in the shape of the graph of a given function. So you can see also that this is a quadratic, and the resulting graph, previous methods, is a upside down paraboloid, which, in other words, a hill. Okay, so that being given, we are currently right here. Right? We're sitting above 1, 3. And at that point, I want to know which way is uphill. Right? Now, before I get into answering that question, I do want to recognize a notational awkwardness. You'll notice I say I'm at the point sitting above 1, 3. So 1, 3, if you were to put it on this picture, you'd probably think of it in terms of being down here in the XY plane. After all, there is no Z coordinate, and so we're, think of it this way. If you were to describe your location on a map, right, you give map coordinates, longitude and latitude, that's kind of analogous to X and Y, right? And if someone were to call me on the phone and said, hey, where are you? And if I were to give them my location, I would give them, roughly speaking, my X and Y coordinates. I wouldn't tell them, and by the way, I'm at approximately 300 feet above sea level. Right? Of course I am. Right, I'm on the surface of the Earth. That's how high the surface of the Earth is at this longitude and latitude. So it's sort of unnecessary. Right? So just be aware before we get into the solution to this question, very often these 2 points, namely the point in the domain and the point on the graph sitting above, if you will, the point in the domain. Very often we kind of blur the distinction between these 2 points, and we just kind of talk about them as if they're the same thing. And again, I think this is pretty reasonable. Again, if you're looking at a map, you're not even looking at height, right? And you infer your height from, well, you're on the surface of the Earth. Okay. All right. So, when the question says, which direction is uphill, again, you have to interpret this appropriately, uphill in the map sense. So, sure, I am here, right? But if we were to talk about uphill, then we would say, well, here's where I am on the map, and uphill would be that direction on the map. And of course, technically, I suppose, uphill from where I actually am is actually kind of like that, but nobody wants to know that. Right? If you want to know which direction is uphill, we're typically talking about map directions. I hope that makes sense. Okay. So we want to know this direction right there. Okay, so now that we've got the terminology out of the way, the answer, of course, sitting right here above us on the page. Direction of fastest increase, aka direction of steepest descent, aka the direction of uphill. It's just the direction of the gradient vector. Yeah, question.
Wait, so are you saying that it's the direction in the xy plane that is towards the highest one, I guess?
No. So I can see why you'd think that, but it's not always the case, right? So the direction of steepest descent says, okay, here's where I am right now, and I'm myopically looking only within just a few feet of where I actually am, and based on where I actually am, maybe that's uphill, and maybe that's a contour line, and then that's downhill down that way. Right now, the actual top of the mountain might be over there, right? Because mountains aren't perfectly symmetric, like this one happens to be coincidentally, right? Mm-hmm. So, in general, uphill does not mean which direction is the mountaintop. Okay. It just means, again, sort of looking only within a very short distance, looking only in that, this very narrow area. Just here, which direction is uphill.
Okay.
Is that cool?
Yeah, so and that's so basically within a close radius, which is the steepest. Yep. In terms of Z. Z, right?
Yeah, what makes Z increase as fast as possible. Okay. Yep. More to the point, what makes the function increase as fast as possible, but if you're looking at the graph, then the value of function is Z. Yeah. Right. Okay. So, sorry.
Would it be the same as projecting that original vector onto the XY plane?
You're talking about the actual uphill vector?
Yeah.
Yeah, kind of.
Would the direction of that onto the XY plane be the direction if you were looking at it?
Yes, that's right. Exactly. Not particularly useful information though, because this vector we don't know how to find it anyway. Yeah. But yes, that is true. Yeah. Okay. All right. So how do we find the uphill direction? Well, uphill is in the direction of the gradient, so it's that way. Right, I guess you could make that a unit vector. Not that big a deal. Watch the coordinates.
I'm sorry.
That's all right. No worries. Not a problem. Okay. Let's see here. So whether it's a unit vector or not super big deal. Typically we think of unit vectors as describing directions, but minor point. Okay, now how steep is it? Well, again, how steep is the hill? The steepness of the graph is that maximum directional derivative is the magnitude of the gradient. And so, again, we've already computed the gradient, so the magnitude of the gradient, also easy to compute. Okay. How are we doing? Yeah.
For circularly generated shapes like this one, is the direction always going to be directly towards the center?
It'll either be directly towards or directly away. Yeah, right. But that's a very very narrow collection of cases. And on an exam, I wouldn't want you to cite that because we haven't proved that, right? But just for curiosity's sake, yeah, that's true. Yeah, right. Okay, everybody, all right? Okay. Let's talk about level sets. We know a little bit of calculus of level sets. Not a whole lot, really. We have this loose understanding of how the separation between the contour lines says something about the value of the partial derivatives. The closer they are together in that direction, the steeper it is, right? The higher the value of that partial derivative. So we're going to learn some more now, more calculus of level sets, and it's going to come by thinking through a certain scenario. Suppose we're looking at a level set. So level set called S. It's the level set where the value of some function f is a constant c. Whatever, it doesn't matter what the constant is. And here's the thing. If you are on that level set, if you're on that surface, what's the value of f there? Well, the whole point to the surface is that the value of the function is always c. So the value of the function is c at that point. Now, what if I move along the surface? Let's say I move kind of like this along that surface. Keyword along the surface. Everywhere I move on this surface, on this purple path here, I'm staying on the surface. That means the value of f always c as I move along this red path. And so, how fast is the function changing per unit distance as I move along that curve? Well, it's not changing. It's c, right? So that derivative is equal to 0. Well, that means, if you think about it, as I move with this velocity, that velocity being a tangent vector. Forget about the curve now. As I move with this velocity. Well, because it's a tangent vector, this is literally the velocity that I have as I'm moving along that parametric curve that we just described. Right? So this is really a repetition of the same question. If I'm at that point and moving with velocity being a tangent vector, again, function's not changing, at least in the instant. So df ds is equal to 0 for all tangent vectors. And now, here's the thing though, df ds is the directional derivative. And directional derivatives are computed with that dot product. So when I say that this df ds is equal to 0, that means the directional derivative is 0. That means that this dot product is equal to 0. And if you think about that, what does it mean for a dot product to be 0? That means that the two vectors in question are perpendicular. Right? So the gradient is perpendicular, orthogonal, to be fair, orthogonal to all the tangent vectors. And so now let's draw that picture. All right, so here's my tangent vectors. That's a tangent vector. That's a tangent vector. All of these vectors here are all tangent vectors. In fact, this entire tangent plane, any vector parallel to that entire tangent plane, all tangent vectors. And I know that the gradient is orthogonal to all of them. And if you think about it, if you've got a vector that is orthogonal to all tangent vectors, wouldn't it stand to reason to claim that this gradient vector would then have to be perpendicular to the surface itself? Seem like a reasonable conclusion? So this is actually really powerful fact. Gradients are always perpendicular to level sets. So really useful information. And now this is, again, what I'm going to call important part of the calculus of level sets. Calculus, because we're talking about gradient vectors, which are computed with derivatives, right? So that's calculus. But from the point of view of understanding the function in terms of its level sets. Okay, so really important fact. Let me show you one thing we can do with this. Now, this is arguably old news, but it's a new point of view on an old thing. We're going to talk about tangent planes. Previously, we understood a tangent plane in the context of thinking of it as being a graph. So, for example, if you have some function of two variables, x and y, you look at the graph, you get a surface in space like this, and you can talk about the tangent plane to that graph. Okay, right. And you would talk about that tangent plane at a certain point, x naught, right? Where is that point x naught? Well, that point is sitting above a certain point in the domain. The point in the domain, let's say, has coordinates a and b, and being as this is on the graph, the third coordinate comes from the function whose graph you're looking at. Yes?
How can you, I'm trying to understand it, more conceptually, why the gradient would be perpendicular to the level set plane, it's that image.
Yeah. So here's some intuition. If you're going along the level set, the function is not changing. Mm-hmm. But if you want to know in general how fast is a function changing as you move, it's always a dot product with the gradient. Mm-hmm. So that dot product with the gradient has to be 0 for all of these tangent vectors. Okay. Does that help?
Yeah.
Okay. Cool. Yeah.
Thank you.
Yeah, sure. Okay, so we've got here's an old point of view. We've got a function. We look at its graph. The graph is a surface. Pick a point on that surface. Talk about what is the equation of the tangent plane. Again, we already know the answer to this question. We got it by thinking about the linear approximations and stuff like that. And the graph, the linear approximation, etc. Okay. So what I want to do now is take a different point of view on this. And that is, let's take this graph, z equals f, and let's reinterpret it as being a level set. Not of f, of course. Level set of f is a totally different thing. Level set of f would be curves in the xy plane, for one thing. But this graph, by doing this little algebraic trickery that we've talked about before, right? You just kind of move one term over to the other side of the equation. You can see it right here. This is a level set, right? I'm setting something equal to a constant. It's a level set of this other function, g. Right? So now let's completely abandon this whole graph point of view. Forget about the graphs. I want to find, apparently now, according to this, I want to find a tangent plane to a level set. The fact that it originally came to us as a graph, whatever. Let's, set that. Who cares? I want to think of it as a level set now. And tangent plane to a level set? Well, how would we find a tangent plane to a level? Well, I need to find a normal vector. Need to find something to serve as our in. What is it that would be a good normal vector? I need something that's perpendicular to that tangent plane. In other words, I need something that's, in fact, it's perpendicular to this surface. Don't forget, though, this surface I'm now viewing as a level set. So I need a vector that's perpendicular to a level set. And that's exactly this tool that I have right here. Gradients are always perpendicular to level sets. Yeah? So, you want a vector perpendicular to a level set? Great, use the gradient. Specifically, it's going to be the gradient of this function whose level set we're looking at. And at this point, it's all downhill. It's all over but the shouting. We do have to compute a couple of things. Let's see here. We're going to need to compute the gradient itself. So we're going to have to take the various partials of that function. X partial, Y partial. Z partial, of course, is easy. The Z partial of this expression, there's only one term that even has a Z in it. It's just Z. So the Z partial is just 1. Once you've got your normal vector, right, here's the equation of a plane. Normal vector goes right there. As usual, X is XYZ. We do need, of course, to cite the point we observed previously, x naught, a point that's actually on that surface, a comma b comma f of ab, talked about previously, and multiply it out, and we're good. This is the equation of a plane, and if you in particular solve for z, then what you get is this formula. As said differently, we reproduce the old news fact that tangent planes relate to the linear approximations, and more to the point, tangent planes are graphs of linear approximations. So, old result, nothing new in terms of the result, but a new approach, a new way to think about how to derive that. Okay, just as an example. An example kind of, this is an example of the argument, not an example of the result, but an example of this argument. Let's suppose you're interested in looking at the graph of this function right here. Function of two variables, so the graph is a surface. Want to find the tangent plane at this point here. Well, of course, this point P, it says above 2, 1. That means that 2, 1 are the x and y coordinates. But the point above that, of course, also has a z coordinate. And in order to find what that z coordinate is, I've actually got to take that and plug it in and see what the function becomes. Becomes 4. A little bit of arithmetic there. So there's our point. Got our point on our surface given as a graph. So again, being a graph, that means z equals. Right, so there's our equation describing the graph. Now I'm going to pull the exact same little fast one that we did on the previous page and point out that, if you just move things around a little bit, nothing really, hardly anything happened here, just moving terms around, but rewritten as it is, I can interpret this now as being a level set. And specifically, it's a level set of that function g right there. And that function g, you can compute its gradient. Once you know the gradient, you've got a normal vector. All right, let's, maybe I'm moving a little too fast. There's the gradient of g. Plugging in the point in question gives me this. It's just arithmetic. And once you have your normal vector, and of course we already have from before, we have the point, multiply it out, and there's your tangent plane. Everybody okay? Okay, if I can get this to work. There we go. Okay, real quick observation. This question presumed that we started off with a graph, and the very first thing I did was turn a graph into a level set. So, heads up though, sometimes the question will actually have that part done for you. If the question might be, find the tangent plane to some surface where they just give you an equation. Right? And if you have an equation, again, keep in mind you can move terms around however you like. If you have an equation, it's kind of already written as a level set. Just make sure that the terms are moved around in such a way that you have a constant on one side. And then same approach from there on out. You identify what the function is, whose level set you're looking at, take the gradient, blah, 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 and you're done. Okay. All right. So this is not exclusive to graphs. This works for any time you have a surface described by an equation. Okay. So moving along. We're going to talk about the implicit function theorem and implicit differentiation. I think y'all might have seen some of this in high school calculus classes, single variable classes. Usually, high school calculus classes don't have the tools to give a proper treatment of this. And they also, even if they did, probably wouldn't do so anyway. So there's some subtle questions to implicit differentiation, and I want to make sure that you've at least been exposed to the big ideas. I'm not going to be rigorous about this. In fact, I'm going to be pretty non-rigorous in this discussion. But it is important to entertain, to realize the sophisticated questions at hand. So now we've talked previously, in fact just a few minutes ago, every time you have a graph, you can choose to view it as a level set. The opposite question, if you have a level set, is it necessarily a graph? We know the answer is not in general. Right? It might be, you might get lucky, coincidence, right? But typically, generically, no. Right? Not every level set is a graph. So we're going to address a related question. Can I view a level set? Here's a level set. I'm going to just do this and start off in 2 dimensions. There's a level set. Can I view it locally as a graph? And by locally, what I mean is, given a point, let's say this one here, locally says, okay, I'm going to look at some small neighborhood of the point in question. Just that small neighborhood. I'm going to ignore every part of the curve other than this small neighborhood. So I'm going to look just at that one little bit of the curve and forget about all the rest of it. We're going to ignore all of that. Right? Looking just at this little piece of curve. In other words, locally. Can I view this part of that level set as being a graph? Can I view y as being a function of x? In other words. And by the way, looking at this picture, I think it's pretty clear the answer is yes, right? Think about the vertical line test. The vertical line test, no problem. Is everybody happy? Okay. All right. Now, let's ask the same question about, let's see here, about this point right there. And it's tempting to say no, fail, because vertical line fails, right? But keep in mind, that's not the question we're asking. What I'm asking is locally. In other words, looking just at a small neighborhood there. And by the way, the answerer to this question gets to decide how small this neighborhood is. So you don't have to worry about, what if the neighborhood were that big? Then we'd have a problem. Yeah, okay, then don't pick a neighborhood that big. Pick the smallest neighborhood that you can. Small enough to solve any concerns that you might have. So again, locally, around that point, we're talking about this little piece of curve. And that little piece of curve passes the vertical line test, no problem, no issues. Again, don't worry about these intersections up here. They don't count. It's not even there. I'm not even looking at that part of curve because I'm looking locally. Is everybody with me? Everybody happy? Okay. All right. So it's tempting to say, all right, well, just keep making your neighborhoods, just make them as small as you need to so that the answer is always yes. And, so I've got an intersection there and I want to worry about this intersection. Okay, well then just choose your locally to be smaller than that is and no problem. Tempting, but no, because let's think now about this point right there, by which I mean the point where, as I'm going from top up here, the point where my velocity is straight down. In other words, the point where the water kind of separates from the cliff in the waterfall, as it were. Right? At that point, no matter how small your neighborhood is, doesn't even matter how small your neighborhood is, if you look at the curve, same equation, you look at that curve, in the vicinity of that point, you're going to fail the vertical line test. Right? So like there, it intersects twice. Everybody see the problem? Okay. So locally, At this point, we're good. We can think of y as a function of x. At this point, I can think of y as a function of x locally, I emphasize. At this point, nope. And it doesn't matter how small your neighborhood is. Make it as small as you want. The curve is kind of wrapping under itself, and somewhere you're going to have this failure. So at this point here, not even locally can you view y as being a function of x. All right. Now, let's ask the question of who cares. Why are we doing this? Are we just some exercise in mathematical formality? And this is this is an important point. Keep in mind that if you want to talk about a derivative, right, dy dx, to even be able to write that down, not for this to exist, right, but for this to even be a thing, for this to even be a question, right, independent of whether there's an answer, but to even be a question, hey, what is dy dx? You have to first establish that this thing is a function. You can't take the derivative of just kind of, anything that you feel like, right? My favorite silly example, you cannot take the derivative of bicycle. That doesn't make any sense, right? And you cannot take the derivative of y if y is not a function, right? So until you know that y actually is a function, at least locally, right? I mean, it'd be good enough it was a function at least just a little bit like, so for example here, if I'm interested in dy dx at this point, well, at this point, locally is good enough. If you're thinking about the slope of the tangent line, I only need just a little bit of curve. I don't need curve way up here to define a tangent line at that point, right? So, at least locally is good enough. But, again, in some cases, for some points, the answer here is no. For a point like this, y is not a function. So there is no such thing as dy dx. Again, not that dy dx is a reasonable question to ask and it just turns out to not exist. It's worse than that. It's that there is no such thing in the first place. Okay. All right. So we need to be able to figure out how to distinguish cases like this where y is not a function of x, not even locally, from cases like this, where, well, yeah, sure, I might not be able to solve for y, but yeah, sure, y is a function of x locally, and feel free to go ahead and talk about dy dx all you want at a point like that. Okay. So the way we answer this question, again, this is where I'm going to be quick and dirty. Good enough. I just want to leave you all with the intuition of morally what's going on here. And morally what's going on is if you have a problem, then I claim, again, intuitive hand waving. The way a problem comes up is by the curve kind of being in the process of wrapping under itself, right? I mean, that's what allows for this scenario. The vertical line test is always going to fail. I need at that point, I need that to be the point, the instant where the curve has begun wrapping under itself. If that's the case, claim we're going to have a vertical tangent line. And if we have a vertical tangent line, keeping in mind, don't forget, our curve is a level set. We have a level set with a vertical tangent line, and keep in mind that gradients are always perpendicular to level sets. That means that we have a horizontal gradient, and of course the gradient is made up of various partial derivatives, and if it's horizontal, that means that the second coordinate must be 0, and so partial of f with respect to y must be 0. So let me summarize all of this argument then as follows. If you have a problem, and again, keep in mind, this is what problems look like. If you have a problem, then it follows that the y partial is equal to 0. Right? Problem. We conclude that y partial is 0. And now what I'm going to do is I'm going to remind you all of this logical construction called the contrapositive. If P implies Q, then not Q implies not P. Right? And so the contrapositive of this statement is this statement right here. As long as that y partial is non-zero, there couldn't possibly be a problem. Right? And again, just thinking through what how the contrapositive makes sense in this scenario. If the y partial was 0, but there were a problem, if there were a problem, the y partial would have to be 0, and that's incompatible with the presumption here that the y partial is not 0. So, the y partial is not 0, no problem. So, this is the implicit function theorem. This is, I guess you could call this the single variable implicit function theorem. It does involve a partial derivative. The argument that I've given you here at least involves gradients. So again, they don't have the tools in Calc 1 classes to be able to do this. But it remains that if you want to establish that you can in fact even begin talking about implicit differentiation, you need to establish that you actually can view that thing as being a function. In other words, you need to do this first. Otherwise, what you're writing down is garbage. Okay, so now here's the three-dimensional version. And it's shockingly similar as an argument. So again, suppose you have an equation of three variables. An equation of three variables would give you a surface. Something like that, right? And again, you're viewing this as a level set. We want to ask the question, though, can I perhaps view z as being a function? Again, no assumption that this is going to work. Z is not given as a function. Z is given as a variable. It's one of three variables in an equation that gives me a surface. No reason to believe that z is a function here. Okay. Well, let's ask, can I view z as a function? Well, how about, for example, at this point here, and again, thinking locally, looking only sort of nearby that point, looking at just this part of the surface, can I view z as a function of x and y? Yeah, no problem. I don't have to worry about this part of the surface down here. We're only looking locally. And that basically gives me just a nice little piece of surface that passes the vertical line test. No issue. No problem. However, at this point, no such luck. At that point, right, our surface, kind of like what I have here in my hand, right? If you're at that point, that's where the surface is in the process of wrapping under itself. Right? That means no matter how locally I look, I'm gonna fail the vertical line test because the surface has wrapped under itself and you're gonna have multiple intersections. So, how do I detect problems like this? The problem, again, highlighter, the problem is that the surface is wrapping under itself. If the surface is wrapping under itself, then it's going to have a vertical tangent plane. And if it has a vertical tangent plane, then the gradient must be horizontal. And another way to say that, horizontal means that its third coordinate, the horizontal means that its third coordinate would have to be 0. Everybody on board? Notice how this argument is morally not that different from this argument here. This is just kind of a three-dimensional version of that previous argument. So again, contrapositive, problem implies that this partial is equal to 0. The contrapositive then would be as long as this z partial is not 0, then we can't have any sort of a problem. All right, and so here's the, and real quick, before I get to the final statement. Notice that, again, the variable that I want to view as a function is the one with respect to which I need to take a partial and, hope that that partial is not 0. Okay, yes?
Does that say, anything about the
or being a function of y only and it's not a function of x?
I'm having a little trouble hearing you volume-wise. Sorry.
So that
Mm-hmm.
if f over z is
Yep.
0,
Yep.
that means that z isn't a function of x.
So keep in mind what we've got here. We've got an equation involving three variables. An equation involving three variables is going to look something like this: blah equals blah, right? And I'm going to rewrite that though. Always rewrite as a level set where subtract stuff to the other side, right? And this is the function. That's the function I need to be taking partials of. The function whose level set describes my surface. That's what I want to take the partial of with respect to z. I'm not sure though if I answered your question.
I was, because in the other example it meant that it's not a function of x. So I was wondering since it's
Oh yeah, okay. So let me come back up to this other example. So in this scenario here, right, locally I can't view y as being a function. Right now, function of what? Well, function of all the other variables. Well, of course, there is only one other variable, right? So because there's only two variables total, what we've eliminated here is the possibility that y might be a function of x. In this next scenario here, well, there's three variables, x, y, and z. And when we entertain the question of whether z is a function, well, what I mean is it a function of the other variables? And the other variables in this case are both x and y. Did that answer your question?
Yeah.
Okay, cool. Yeah. Okay, all right. So, real quick, again, the variable that you want to view as being a function, take the partial of f with respect to that variable. Okay, so in general then, here's our implicit function theorem. And again, if you have a level set, very critically, it's got to be a level set. Right? Written as a level set, this function over here being the function whose level set you're looking at. If the partial with respect to one of the variables, whichever one you're interested in, if that partial is non-zero, then that variable you can locally view as being a function of the others. And I'm not going to prove this again, but again, hopefully you notice the pattern. I mean, that held for the two variable case. That's the conclusion we've got here for the three variable case, and I'm just going to wave my hands and say pattern continues, and I believe this is a believable result. And again, you take the partial with respect to the variable that you want to view as being a function. That's how you remember it. Okay. All right. So let's see an example in action. Here is an equation. Bit of a ugly equation, right? If you were to ask me to draw a picture of this surface, I would fail. If you were to ask me to give you any intuitive sense of what this surface looks like, again, fail. I have no idea. This is a really weird equation. I don't know what this thing looks like. But I can readily answer this question. Is x locally a function of y? And now again, locally, right? Locally near, we're looking at this point here, 1, 2, 3, which by the way, you can confirm for yourself is on the surface. Arithmetic, plug it in, equation works. Okay, so is x locally a function? Again, the variable that I want to view as being a function is the variable that I take the partial with respect to. The function whose level set I'm looking at, that's the function that you take the partial of. All right. Make sure your surface is written as a level set of a function. Take a partial of that function and take that partial specifically with respect to whichever variable you're trying to decide if it's going to be a function. Okay, and so a little bit of algebra. The partial derivative is this. You evaluate at the point in question. Let's see, 1, 2, 3. We plug that in to this partial derivative, the value is 4, which is not 0. Not 0 means no problem. And we're good. Is x locally a function? Yes, it is. Everybody good? It's very plug and chug. Just have to make sure to interpret everything correctly. Okay. All right. So now here's a harder question. How do I take a derivative of this new function? Right? So we come back up here to this, what we just looked at. Apparently x is some sort of a function of y and z. So I'm legally allowed to write down the expression partial of x with respect to y, because x is locally a function of y and z. So I can say partial of x with respect to y. That's not garbage. But the problem that remains is, how would I compute that? How do I find it? How do I actually find what that thing is? Okay. There's different approaches that you can take to this. I'm going to show you my favorite one. By the way, I'm going to presume that it's already been established that we're looking at a level set. It's already been computed what the partial is of the function f, thus establishing that the thing I want to take a derivative of is indeed a function. Let's make sure this is all already settled. And this thing that is a function, I want to take its partial with respect to, let's say, xj, whatever, one of those variables. Oh, yes.
In questions like on test or like homework, do we always need to verify to make sure before taking a derivative?
Absolutely. Yeah.
Differentiable?
Absolutely, and I'm going to hit that point pretty hard in a couple seconds here. Yeah, but yes, absolutely. So yeah, more to come on that question. Okay, so how to compute this partial derivative? Again, there's multiple ways to do it. I'm going to say a fully flushed out discussion is in this picture right here, this diagram, this algebra. But the thing about it is, this is uglier than it really needs to be. So I'm going to show y'all the streamlined, close enough. I mean, admittedly a little sloppy, but plenty good enough for our purposes. Point of view. And look how much simpler that diagram is. So here's the idea. Keep in mind our function f is constant. It's not allowed to change. So I'm going to say equals 0. Any constant is fine, but I like 0. I've got all these variables. X1 through xn. F is a function of all of those variables. However, I am choosing to view xi as being a function of all of these other variables. Right, so kind of a weird diagram. But xi is a function of all those other x variables with the understanding that f remains constant at 0. Okay, so I'm going to ask the question then, what happens when xj changes? So as xj changes, what happens? Well, two things happen when xj changes. For one thing, xj changes immediately and directly contribute a change to f. Right? F is directly a function of xj, so we get a term there, partial of f with respect to xj. But here's the other thing, though. In addition to that, as xj changes, it will also be the case that changes to xj will cause changes to xi, and changes to xi will also contribute changes to f. Right? So when you wiggle this one, right? You tweak this variable xj a little bit, and keep track of how those changes propagate. Well, xj changes are going to cause that to change directly, but it's also going to cause xi to change, which itself is going to cause f to change as well. And yet, it remains that f is not allowed to change at all. It's constant. We're stuck at f equals 0. So grand total, altogether, the sum of these change altogether, the total change in f, the sum of these two contributions, has to be 0 because f isn't changing. So that gives us an equation to solve. And if you take this, let me just clean up the mess here. Take this equation here and solve for what we were interested in. There it is. I was interested in partial of xi with respect to xj. And there it is. Nice and convenient. And this is a convenient tool to have. Now, a lot of students get thrown by this minus sign. A lot of students feel like, well, that way that doesn't seem right. In fact, shouldn't that partial f and that partial f, shouldn't those cancel? Right? Now, remember, we've already talked about how, no, you can't do that. That's not a thing. These are not the same thing. This partial f, that partial f, they are participants in different stories. Very different stories. In the numerator, that says xj is a variable, xi is a constant, and then I want to keep track of how much f changes. But down here, those roles are reversed. Totally different story, totally different scenario. Now xi is a variable and xj is a constant. So these two things, and again, the notation, they look the same, partial f. They're not the same thing. This is, Steve from one book that you're reading. This is Steve from a different book by a different author, totally different person. They're just not the same at all, right? So don't fall for that mistaken sort of cancellation thing. Do notice, though, for your convenience, that other than that minus sign, it's as if those cancel and the denominator of my denominator becomes a numerator, and it really looks like it kind of sort of works. You can use this as a memory tool. Feel free to use it as a memory tool. The way you're going to remember this equation is it's, kind of what you would think it ought to be, just don't forget that minus sign. Okay. I guess we'll have to call it here. We're out of time. Pick up here on Friday. See you later. Have a good one. Oh, and stick around if I didn't get your name for attendance yet. Yeah, see you.